Hey, it's great to be here. Welcome to my talk, Canary and the Datamines, using Log Canary to find PII, or personally identifiable information, or just in general sensitive data in logs. So you gave me a great intro, but I'm Ryan Slama, and my pronouns are he, him. I work on the Product Security Foundations team at Slack. I'll get into what that means and what the foundations aspect is in a minute, but first I want to introduce the core problem. So here are some high profile issues that have happened in the news in the past few years where giant companies, including some with the most engineering resources like Facebook and Google, have had sensitive data find its way into logs. More specifically, these examples are all plain text passwords, which is some of the most sensitive data possible. Sensitive data seemingly always finds a way to get into logs, and we're going to talk about today what we can do about that and how we can prevent that. So I promised to talk about product security at Slack, and we've had a bit of an interesting journey. So about 2 years ago, we decided to split our product security operations into two teams. The existing team, now known as Product Security Classics, handles most of the traditional responsibilities of a product security team. This means they handle feature reviews, they manage our bug bounty program, and do penetration testing. We decided to spin off a separate foundations team, which allows us to make more strategic bets and to try to limit the overall risk surface of Slack by creating secure by default libraries and services, focusing on automation, and educating our developers. So, for some context, if you're not familiar, I want to cover what Slack is. Slack is a channel based messaging platform that will integrate with all your tools and services that lets you communicate with your entire team, keep everyone in the loop, and do it all in a secure enterprise grade environment. So, Slack deals with a lot of sensitive data, from message text to all kinds of other things. And we treat all of it at basically the same level of security. Because if someone accidentally posts like a private key into Slack, we need that to be secure too. We even treat emoji names with the same level of security because pretty much every big project at Slack gets custom emoji assigned to it. And if those names leaked, that would be important information about our projects. So basically, all data that you might put into Slack as a user is sensitive to us, and we take huge steps to protect that. Of course, we also protect against the typical things like tokens and passwords and hashes. But we should answer the question, how does sensitive data get into logs? Well, to make a long story short, we put it there. Comprehensive logging is necessary to keep the complicated services of today reliable. Large web apps and production infrastructure have many components, often many services, and a whole lot of complexity. And quite frankly, observability is critical in allowing us to debug issues and resolve incidents quickly. So I want to talk a bit about what observability looks like at Slack. Honestly, we use very standard tooling that you're probably familiar with. We use the Elk stack, which is Elasticsearch, Logstash, and Kibana. And we also use Prometheus as our time series database and Grafana for visualizations and alerts. We use Honeycomb for our distributed tracing. And if you're not familiar with that, it basically allows per request profiling and allows you to see the path that those requests take. And we have many more tools that are outside the scope of this talk because they're not relevant to what we're talking about today. But these are the most important ones and also the ones that you're probably most likely to be familiar with. So with great observability comes great responsibility. When we're logging lots of information, we need to be very careful about what we log, because if sensitive data were to leak into logs, it would be a huge issue. We need to keep our customer data private to maintain the trust that we've worked so hard to earn. And it goes without saying, but protecting tokens and passwords is especially critical because they would enable user impersonation and allow access to all of the other sensitive data. So I want to take a step back and look at where can issues come from. So a lot of they basically come from wherever you can emit logs. So at Slack, we proudly have a giant monolith, and Of course, that comes with a lot of logging. Our application monolith logs lots of information to Logstash. And sometimes it only happens in special cases too. For example, our job queue has special logging in rare edge cases when a job runs out of memory. Some other information, I mentioned honeycomb earlier. You can log information in honeycomb span traces. And there's a long tail of other sources because with a complicated infrastructure, we end up ingesting logs from many sources. And that could be Apache access logs, logs from our caching layer, HA proxy, Chef, or honestly, a million other services. So how can these issues happen? It turns out not logging sensitive data is surprisingly hard because when you're dealing with a code base with millions of lines, it's honestly hard to predict what might be in any given string. And there are ways to limit that risk, which we'll talk about soon, but it's very hard to know for sure. And because of the complexity, when you're dealing with such large systems and such large amounts of code, there can be a number of weird edge cases that produce unexpected results. And at Slack, we deploy many times a day to production, and the code changes very rapidly. So a logging statement that you add to the code today that always logs just IDs or non-sensitive data, it hypothetically could not be okay later on if someone starts calling your function in a way that you didn't expect. So even if you add logging statements today, there's no guarantees that it will be safe going forward. So I want to talk about what we've done historically at Slack to prevent this. So we use Hacklang, which gives us strong typing, which is critical in providing context for the code. Now, I'm not saying we use some fancy IO monad and know exactly what gets logged and where, but strong typing allows developers greater confidence in what sort of data they're dealing with. And likewise, we use documentation to provide information to developers so they know what gets logged and what is sensitive and what is okay to pass in. We focus on education by having rigorous standards that we educate our developers on so they know what counts as sensitive data, so they know what's acceptable to log. And we do a lot of this code review too. So there are tools that automatically will look for certain patterns in the code and warn developers if it looks like they're logging something that might be potentially sensitive. And we also have manual people who look at that too. Additionally, we use automatic log sanitization with scripts so that even if some information were to make it past all of the above mitigations, we try to automatically sanitize it and remove it before it ever reaches logs in the first place. But today's talk really isn't about any of those other points. Today, we're going to look at instrumenting and alerting as ways to catch issues before they reach production so we can limit any impact. So our solution is Log Canary, and it looks something like this. Well, not quite. So the core insight is, what if we pretend to be a user? So we created a service that interacts with the Slack API, both public and private endpoints, and it pretends to be a user. We make various requests with data to our API. And what we do is we include a canary string on those requests. And a canary string, as you can see on the slide, is just a long random string that should never accidentally appear in logs. That way, we then search logs for those canary strings that we hit the API endpoints with. And we know if those canary strings ever do end up in logs, then we have a problem. And this has the benefits of being 100% true positives. There's no way a canary string will appear in logs and not be an issue. So it allows us a great deal of confidence in our system and our alerts. So I want to step back and think, where do we run the tests? So option one is probably what you'd think of first. We'll run it with all our normal API tests. Maybe we can mock out our logger and have it automatically check if a canary string is included in anything that's passed into the logs. And if so, we'll just fail the test. And that's a good start. And it can issues very quickly as part of your typical test run suite and at PR time. But today I'm going to talk about option two, testing in production. Because it turns out the best way to mirror your production circumstances is to actually run against production. So logging is a funny thing. Oftentimes, logging paths don't happen when everything goes right. We log in exceptional circumstances, when things are weird. And the problem with testing environments is they're very normal. In order to remove any flakiness, they're very controlled environments that always run exactly the same. So these controlled environments can miss edge cases that could occur in production. Additionally, running real API calls over our servers allows us to span the entire request, from load balancers to Apache to our routing and the database code. So it's more than just an integration test. We actually can span the entire request and know if at any point sensitive data gets logged. So as an example, at Slack, we use Vitess, which is a database clustering system for MySQL. It was originally created by YouTube, and now it's used at a number of tech companies, including Pinterest, Square, GitHub, and many others. Log Canary quickly caught a massive issue that only manifested during shard splits that otherwise would have gone unnoticed. Because of Log Canary, we were able to mitigate the impact, and it resulted in a patch being merged upstream to Vitess, which means Log Canary has actually already had an impact outside of Slack. So I want to go a bit into some of the implementation details and talk about how we actually built this. So first, when setting out, we wanted to figure out what would make a good implementation. We wanted something completely automatic. Because these issues are rare, we wanted something that we could set up and forget. It wouldn't require any manual interaction, and we would have confidence in our code paths. We wanted to detect issues rapidly, so it would let us know exactly when something happened. Additionally, the notifications should be actionable. There's no point in knowing we have a problem if we don't know what the next steps are and what to do about it. And at Slack, unsurprisingly, we're big users of Slack. So it made sense to pipe the alerts right into a Slack channel where we work and where we get the rest of our information. So I've actually included an example alert on this slide. And you can see that not only do we show the number of logs, but we also have a link to a query. So we can view the logs in Logstash and investigate where they come from. Slack threads provide a great way for us to discuss these issues in line. So if any discussion is needed, we can tag the right people, bring them into the discussion, and figure out the fastest way to remediate the issue. So how did we do this? We built out a tool in two parts. So the first part is a headless microservice that executes requests. So basically, we defined a number of canaries, which were arbitrary blocks of code that call APIs with the canary strings. And we run these at a regular cadence, so we know when the information does end up in logs. And the second part is a Grafana dashboard. The Grafana dashboard automatically queries our logging infrastructure and shows graphs with canary strings over time. So if they do show up, we can know exactly when it came out. We can figure out, say, which PRs were in the group that were deployed when the issue started happening. And Grafana also gives us alerting features for free. So I want to talk a bit more about Log Canary, the service. So it's actually very simple. We have a data structure, which is just a list of canaries that we run. And each canary is an arbitrary block of code that can run API calls. So an example canary that we run is we post a message to Slack, and then we'll add a message to that thread that's created based on the ID of the timestamp returned to us. And we call these at configurable intervals, so we can figure out exactly how often we want to be testing our API. And each canary includes bad requests too, because oftentimes logging isn't triggered during the happy path. Logging is triggered when things go wrong, when an ID is invalid, when an invariant is violated. We built the service in Go, and it was a fantastic fit. Go was fast to prototype. It was easy to get running. Deploying it on our microservice infrastructure was super easy. Go's type system reduced errors compared to if we tried to build this in a dynamically typed language like Python. And most importantly, Go routines made running many canaries at the same time effortless, because we can just set it up so they run every interval and it's completely non-blocking. So now to talk about Log Canary, the Grafana dashboard. So we have one graph for each Canary string. That's a side effect of Grafana only allowing one alert per graph. And we send a Slack message to an alerts channel anytime any Canary strings are detected. And each alert includes the quantity of data, the link for faster remediation, and almost all of this behavior was for free. This was extremely easy to implement and took no real time. I do want to talk a bit about the deploy process at Slack. I mentioned that we deploy code many times per day, and we've actually built a very mature process over time. So we have a gradual rollout process where we'll first deploy the PRs to a staging environment to test any changes in a real working Slack instance. Then we roll out to dog food where we use them with the new changes ourselves. Then we have Canary, and then a percentage-based rollout to general availability. Each deploy is shepherded by a deploy commander who's empowered to roll back, cherry pick, or fix forward if any issues do occur, and they can reduce the impact of potential issues. And we have a deploy dashboard where they monitor these issues, and using Grafana allows Log Canary to integrate with the existing process. So here's a bit something like what the deploy dashboard looks at Slack. I had to remove some of the graphs here because potentially sensitive information. But because when we're deploying, there is someone watching this, Log Canaries can integrate with the existing process and make sure that we're not actually exposing any new issues. So the pre-existing Canary strings work great for APIs where we can just plug them into the same place. But what about data we can't know in advance? So one Canary that we find to be very important is a login Canary, where we'll log in with a username and password, and then we'll try to make requests using the token that Slack grants us. Slack gives us a new token every time we log in. And since we can't know this token ahead of time, there's no way to just configure a standard Grafana dashboard for that. So the solution that we ended up with was actually just querying Elasticsearch from our microservice. And when we get the token response, after we submit a bunch of requests, we'll then query the recent logs to see if that token appeared anywhere. We use the count functionality, so none of that information ever actually ends up at the Log Canary service, but just enough to post a message to Slack with a link to a log stash query. Our service has its own metrics. We track Canary runs and failures, and we set up alerts on those metrics. So if the Canary runs ever drop, we would get alerted and know that, oh, maybe the Log Canary isn't running as it should be. Maybe it crashed. That hasn't happened. We also alert if the Canary failure rate goes up. So maybe there was an issue with our workspace, or maybe something changed, so we aren't getting the coverage that we expect to. Together, these alerts give us the confidence to let our service run completely autonomously, and no one ever has to think about Log Canary. It just hums away in the background, and if we ever have a problem, we'll get alerted. So I want to talk about the process of what happens when alerts actually fire. The first question is, who answers the call? So our product security team at Slack has a rotating triage duty. And we have a number of tools like Log Canary that pipe alerts directly to Slack. And each day between the two product security teams, there's someone on call who monitors the channel for anyone who has security related questions and any alerts that come in from a variety of our tools. We're also in the process of spinning up a security triage team to help offload some of the burden that comes from having lots of automated tooling. So what happens when we actually do get an alert? So here's the process that we've identified. The first step is investigate the logs that have the Canary string to determine where the sensitive data would be logged. Then we'll try to get a general query that captures the type of error and see to make sure that, oh, is real user data ending up in logs? Then after that, we'll file a JIRA ticket with the relevant owner based on the severity of the type of issue or the type of information in the logs. And exceptional circumstances, such as sensitive customer data, can result in incidents instead. So I want to talk a bit about security tickets at Slack. Luckily, leadership at Slack makes security a top priority, and there's a company-wide objective to close security tickets within SLA, within our surface level agreement. Each security ticket comes with a set time that it must be resolved in, and log canary issues are automatically high or critical based on internal guidelines. For critical issues, we have 7 days to resolve them, and high issues, we have 30 days. And there are special circumstances that result in incidents, which are immediate remediation efforts by cross-functional groups. So I want to step back and review, is this approach effective? And the answer is yes. We've identified issues over Log Canary's lifespan. And the Vitesse patch mentioned earlier means that Log Canary has had an impact even outside of Slack. And Log Canary gives us confidence where we previously had none. But this approach isn't without its limitations. So our coverage is only as good as the code reached by the canaries. We only cover a subset of the Slack's API because the API is, quite frankly, giant. We can't hit all of the code paths because the code is constantly changing. And to keep up with that would be a full-time job for an entire team. And because of the nature of log canaries, we can prove the existence of problems, but never the absence. So I want to talk a bit about some of the future work we're doing in efforts of a brighter future. So one of the core questions is, how can we get complete coverage? And this is a tough issue when you've got such a massive code base that it's impossible for any number of humans to check themselves. So one of the avenues we're looking into is static analysis. Static analysis runs automatically over all the code. So this covers every API endpoint, and it covers every code path. Eventually, this could run at PR time or even show warnings directly in the editor because it's completely automated, and developers can get notified of any potential issues immediately, which makes it significantly easier to resolve because if it's pre-merge, pre-commit, it's just a quick change in the editor and the problem is gone. So here's how we've been looking at it. We've been using some taint analysis tooling, which involves modeling the code base as a flow graph where nodes represent functions. And we track the data flow from sources to sinks. So we mark any functions that we know return sensitive data as sources and any logging functions as sinks. Then we track the flow of data across the code base to see if any data that originates from a source ends up in a sink. So if you look on the image on the right-hand side here, the red node there represents a source. And we can see that a red line passes through a blue function and eventually ends up in a sink. So this would be a problem according to our taint analysis tooling. There are some complications with this approach. Our current code base is dynamic and hard to statically analyze. But fortunately, we're in the middle of a large restructure project that will significantly improve this, and we're already seeing payoffs there. We've got a proof of concept. The good news is our taint analysis tooling works and detects example issues that I've added to the code. And depending on how you look at it, the better news is we found no real issues with it yet. And it also has a very low false positive rate. There's maybe 1 or 2 things that it's flagged, and then upon investigation, it hasn't actually been a real issue. One of the downsides of this approach is right now, it takes way too long to run and way too much compute. So we definitely can't run this on our developers' machines because it's way too long to show information in the editor and even too long to be a blocking test on PRs. So our current approach with some of the existing applications of taint analysis has been a continuous integration job that will run daily scans with our taint analysis tooling. Then the security team manually looks at those findings for results in the meantime. Other applications of our taint analysis has resulted in valuable findings, but there's been nothing related to logs yet. And that's about it for my presentation. So thank you very much. We are hiring on Slack security team. Come build stuff with us at slack.com/careers.